Point 4 is going to ask you for the average rate of change of a function. So let's understand that in a couple different ways. The average rate of change of function sounds pretty impressive, doesn't it? Average rate of change of a function. Well, it's not really that deep of a concept. What you're going to do is you're going to look at a function at two different points along its curve. One, say, at A and one at B. You're going to see how much it changes in the y direction compared to how much it changes in the x direction. And here is your average rate of change, f of b minus f of a over b minus a. They call that the secant line, and what we're looking for is the slope of that line. But this goes by a much more familiar name. Does anyone recognize what you're finding here? Yeah, just a slope. It's just a slope of the line. Now, they call it the average rate of change because initially the function's increasing faster and then it slows down towards this point. So it's not increasing at this level all the way through. It's just on average, that's how it's increasing. So that's why they're calling this the average rate of change. But in fact, it really just boils down to finding the slope of a line between 2 points. Let's start with problem number 16. There's a couple ways you can do this. Problem 16 gives us this function, f of z equals 1 minus 3z squared, and they want us to find the average rate of change between z equal negative 2 and z equals 0. And they give that to you. They have to. Z equals negative 2, z equals 0. What I would suggest is that we handle things like this with a little t-table. You don't have to. Not a big deal, particularly with this one. So that should be a z and f of z. Thank you. There, finally got it. So at negative 2 and at 0, let's put those in there and find what those coordinates are. So if I put in, let's start with a 0. What's f of 0? 1. And let's find f of negative 2. It's going to be 1 minus 3 times negative 2 squared, which is 1 minus 3 times 4. Negative 11. So realistically, what you're finding then for the average rate of change is the slope of a line between these 2 points, between negative 2 and negative 11, and between 0 and 1. Hopefully that formula is kind of familiar to you. We call this x1, y1 and x2, y2. The slope of a line is just the difference in the y coordinates divided by the difference in the x coordinates. In this case, 1 minus negative 11 over 0 minus negative 2. So I get 12 over 2, which is 6, is the average rate of change of the function. Let's take a quick look at the graph and see if that makes sense. So let me cut back over to Desmos. No, that's not it. So let's take a look at the graph. Y equals 1 minus 3x squared. And we want to look at the function at two different points. One here at 0, and the other one at x equals negative 2, which is going to be down here someplace. Still need to go a little farther. Down there, negative 2. But even though I'm not exactly on the point, you can see that the slope of the line here on average is going to have to be positive. As you move from left to right, you're increasing. So the fact that we got a positive answer makes sense. Now with this one, it was easy just to plug in values by hand to do it. Sometimes it's more convenient to make your calculator do the work for you. So it kind of depends on how motivated you are and just how ugly the function is. Let me show you how to do it on a calculator in case you feel, a little underwhelmed by the prospect of plugging in these numbers by hand. So g of x is 2 minus 2/3. And I want to take a look at this at 2 points, at x equal -3 and x equal 2. So I want to find the average rate of change of the function for those 2 points. Well, we can make our calculator do the work. So let's plug in our function 2. So hit the y equals key. 2 minus 2/3 x. Now I'm going to write that minus 2/3 x in a convenient way. So it's going to be minus 2x divided by 3. That's equivalent to what I have here. It's just easier to input that into my calculator. 2 minus 2x divided by 3. Now let's go to our table. Have we taken the time to set up our tables so that we can choose our points? Yeah. We did that the other day. In case you didn't, second and then the window key, make sure your independent is set to ask. If not, go over to ask with the cursor, press enter, then hit the second key and then the graph key, which gets you to the table. We want to examine this function at a couple points at -3 and at 2. Now I'll delete those other 2 points with the delete key, second row down. So at -3, I get 4. Can anyone recognize what 0.666667 is? 2/3. So let's write it with the exact number as opposed to a decimal. -3, 4, and 2 and 2/3. Let's find the slope of the line between these 2 points. x1, y1, x2, y2. 2/3 minus 4 over 2 minus -3. Doesn't look too fun. 2/3 minus 4 in the numerator is going to give me -3 1/3. I could also think of that as being -10/3 divided by 5. To finish this up, let's think of that 5 as being 5 over 1. So now I have the division of 2 fractions. What do you do when you divide by a fraction? Good. Multiply by the reciprocal. Thank you. So that's going to be -10/3 times 1/5. Yep. So that cancels and are left with -2/3. It's not a coincidence that -2/3 is really the slope of this line, because on average a straight line is going to change in accordance with its slope. It doesn't kind of go up and down, accelerate or decelerate. It's just steady. Its average rate of change is just going to be the slope, always. Yes. No. With this one you could, but I would suggest you stick with the values that they gave you here. Yeah. Yeah, they or I will give you the values for which you want the average value. All right? Anything else on problem 14 here? take a look at problem number 28. So I talked a little bit about your rate of change, your average rate of change. And we've got three different functions here, but we want to discuss what's happening to their average rate of change. So let's look at the first one. And they're going to want you to look at it in three different intervals. From 0 to 1, from 1 to 2, and from 2 to 3. What's the rate of change going to be like in each of these intervals successively? 0, 1, 1, 2, 2, 3. What's happening to the rate of change? Staying the same. It's constant. It's not getting bigger any faster or smaller as you move from left to right. It's just a steady or constant rate of change. How about the next one? Is there much change in the function in the first interval? No, not a lot. Is it increasing or decreasing in the first interval? Increasing. And it's increasing in the next one. But if you look at the next one, what can we say about the average rate of change? It's increasing, right? It's changing more in this interval than this one. How about the next one after that, between 2 and 3? It's increasing yet some more, right? So basically it's kind of accelerating. It's getting faster and faster and faster. In fact, have you ever seen a video go viral? It seems viral. I mean, they got websites for that stuff now. But this is kind of what a viral video is like in terms of the number of views. It starts out, a few people see it, and then they tell all their friends, and they tell all their friends, etc. And pretty soon it catches fire. It just explodes. In fact, I think Gangnam Style was the first video to exceed 1 billion views on YouTube. So I wonder what's done that since then. Not sure. All right, so this one's has an increasing rate of average change. This one was constant. How about look at this last function? Now, as you look at this from 0 all the way out to infinity, is this function increasing, decreasing, or what? It's increasing. But the rate of increase slows down. I mean, it starts out really like gangbusters, and then slows down, etc. This is kind of like your growth rate. When you were a baby, you put on a lot of height, and then you slow down. Actually, in near your teen years, you're gonna have another little growth spurt. But initially, it kind of slows down for a while. Yeah, they're growing them big nowadays, man. And some of them. I mean, these linemen you get in the NFL combines are just beasts. I mean, they're 300 pounds and they have a vertical leap of like 30 inches, which is wow. You can, like throwing a refrigerator up in the air by 2.5 feet. It's pretty amazing. Okay, a couple more for this section.
So what would we call the last one?
I'd say that the average rate of change is decreasing. So, I mean, the function is still increasing, but its average rate of change is slowing down.
So even though it's still going up, it's decreasing.
The rate at which it goes up is decreasing. It's still going up, but the rate at which it's going up is decreasing. So, the problem's doing really an elegant job of dancing around a calculus concept called the derivative. And yeah, it's actually pretty cool. You can do some pretty amazing things with calculus. Not sure what our modern world would look like without Isaac Newton and Leibniz's discovery of calculus. Problem 30. Going back to our population growth one. So we've kind of seen this one before. They just have some different questions to ask about it. I'm curious if this actually refers to a real town. The data looks a little bit too clean though. It says, what was the average rate of change of P between x equal 20 and x equal 40? Basically between 1970 and 1990. What's the average rate of change? Zero. It's constant, right? Going from here to here, there's no change. So it's constant. Do you think that accurately describes what's happening here with this function? No. Because you got a maximum and then it decreases a little bit. So that's where you start to need some calculus, because with algebra we can't describe all the nuances of this curve quite so easily. But we're going to keep it to just the problems in the book here. It says, interpret the value of the average rate of change you found in part A. Well, I kind of think we did. There's no change. It stayed the same from 1970 to 1990, at least the average rate of change. But it doesn't really reflect what happened to the population, which peaked in 1975 and then slowly declined there afterwards. Say again? Yeah, they got old. No one was moving in. Their high-tech industry left, and so did all the young people. Yeah, the average rate of change here is 0. Yeah, there's no net change. So when you divide 0 by 20, you're still going to get 0. The average rate of change is 0. Let's take a look at problem number 32. Here they're giving you kind of an incomplete table of number of books in somebody's collection. So between 1980 and 2000, the rare book collection, etc. For his collection at the rate of 40 books a year. Use the information to complete the following table. I think that's pretty simple, right? If he's adding 40 books a year, that's its average rate of change. So how many books would he have in 1982? 500 and 540. Yeah. Right. So it skips a few years here. So what you can do is actually come up with a nice little equation that kind of models this. The average rate of change is really the slope. So y is going to be the number of books. We start out with 420, and then we add 40 a year. So that's going to be 40 times x plus 420. So if I want to find the number of books in any particular year, I just have to figure out how many years past 1980 that I want or need. So for instance, 1995. Okay, well, 95, that's 15 years past 1980. So that means x equals 15. So y would be 40 times 15 plus 420. 600 plus 420 is 1,020. So it'll be 1,020 books in that year. But notice what we're taking advantage of. We're taking advantage of the average rate of change, which is 40. And that's the slope of your linear equation. And likewise, you can figure out any value here for any year once you have that equation. So I think we've got all we need out of problem number 34. One last one I want to look at in this section. Thank you. Problem number 36. So we have farms in the United States between 1850 and 2000. says estimate the rate of change between 1860 and 1890, and 1950 and 1970. So 1860 about here. Let's get rid of that. And 1890. Let's see. That'd be up here. So you're going to have to try and estimate a couple y coordinates and x coordinates for that matter. Now let's call the year 1860 kind of year zero in this process, just to make our life a little bit easier. You don't have to. On the flip side of things, they want us to estimate things between 1950 that's this one here, and 1970, that'd be that one here. So I would estimate the y coordinate here in 1950 is around 5,500. And the y coordinate here in 1970, I don't know. Why don't we, maybe 2,700. Now there's one characteristic that I think that the problem is kind of addressing a little bit, and that is, in which decade did the number of, well, let's see, let's not go there yet. What's happening on average to the number of farms between 1860 and 1890? It's increasing, right? And after the year roughly 1930, then the number of farms starts decreasing. And you can see that by the equation here, sort of dipping down closer and closer to the x-axis. So let's figure out what that average rate of change was. Now I'm not sure about you, but the numbers that I estimated for this, calling this year zero, were 2,000 in 1860, and 30 years later in 1890, about 4,500. Now that's not going to be a perfect, nice even slope, but we'll get something pretty nice out of it. So 4,500 minus 2,000 divided by 30 minus 0. So that'll be 2,500 over 30. Now that simplifies a little bit. Hopefully you've seen this trick before, right? Just cancel out the 0. 250 over 3. It's about 83 1/3. About 83 farms is the slope. It's about 83 farms per year would be what we end up with if you're keeping track of your units. On the other side of things, between 1950 and 1970, I get these points. So 1950 is 90 years past 1860. So my x coordinate is 90, and there's about 5,500 farms here. Whereas in 1970, 20 years later, there's somewhere between 2,500 and 3,000. I just called it 2,700. No special reason there. It's just what it looked like to me. The average rate of change, again, is going to be the slope. So 2,700 minus 5,500 over 110 minus 90. It's important that you subtract the numbers in the numerator in the right order. You should get a negative number. In fact, negative 2,800 divided by 20. The zeros cancel. 2 goes into 280, 140 times. The negative reflects the fact that we're decreasing. So, farms per year, if you're keeping track of the units. I think I remember looking at this data set a little bit more in a stat class, and what was happening at the same time, the number of farms were decreasing, their average size was increasing. So the overall production was staying a little bit more constant. Of course, better farming techniques to allow you to produce even more. But the last question associated with this one is, in which decade did the number of farms experience the greatest rise and the greatest average rate of decline? So where did it drop off most precipitously? Yeah. That rate of decline looks steepest between 1950 and 1960. For homework, try 7 through 19, 29, and 33. I know that's a lot, but I'll give you 5 days to work on it, okay?